Okie dokie, guys. So I think we'll get started. Welcome to everyone at for joining the webinar today. So the topic that we're going to be covering today is going to be, let me find the slide here. So the topic is the Symo hybrid and emergency power, so EPS and backup power. So there's been a lot of questions and discussions around this. It can be a fairly complex topic. I guess we've decided to try and run a webinar in here to try and give us some more explanation and run through the technical requirements for it and how you set it up, etc. The timing, I guess, we've kind of chose at the moment as well is because we've just released the integration with the BYD battery, so the HV, high voltage battery. So it gives you more of a chance to use the Symo hybrid with a few different batteries and also, in this case, do emergency power, so backup. So just a few things to start off with, I guess. So my name's Rod Dewar. I'm joined myself here with Ryan Turner from Tech Support. And so Ryan will be doing questions. So if you've got any questions along the way, or let's say if I start cracking up in terms of the audio or something's not working properly, just shoot that through in the questions column, and Ryan will be able to see that, and he'll let me know. We'll try to fix that up for you. Also, if there's any questions along the way, feel free to shoot them in there. There will be some Q&A time at the end, so depending on how easy the question is, whatever, or let's say there's a few people asking the same question, then usually what we've found is good to do at the end is do that over the actual webinar and talk about it, so I can give you a bit more detailed explanation to certain questions. Okay, all right, so we'll get started. So there you go. That's there's pictures of us, myself, Rod Dewar, and Ryan Turner. So this will be your team for today in the webinar. Okay, so in terms of agenda, the rough outlay of the webinar is going to be approximately as you can see on the screen there. So we'll go through some relevant documentation, or where you can find the documentation to actually implement the EPS function. So we'll go through a lot of instructions and things today, but it may be hard to retain everything, so we have got a whole heap of documentation, so we'll go through that. A little bit about the just the storage options, so Fronius battery storage and the inverter and what's getting used for it. Then a little bit about EPS systems in general as opposed to UPS. Also, what kind of functionalities from the EPS functions you can get from the hybrid, and a little bit about the load capabilities, just so you don't get caught out with different things. We'll go through some hardware and installation requirements through the commissioning, and then we'll actually break down through the schematic to give you a bit of a rundown of, okay, what happens when the grid comes and goes, and backup mode, etc. And also what you can do with dedicated loads. And then at the end, hopefully we'll have some time for some Q&A, if there is some, and we'll ask away. Okay, so in terms of documentation, so through this webinar we're covering how to set up and install and get all the systems going with this. But if there's something you've missed, I mean, what we will do at the end is we will provide you with a PDF copy of this presentation in order to download. The other instructions, etc., on the website, so you can see the fronius.com on the Australian. If you go to downloads, depending on which battery you're possibly using, you can search the word Symo hybrid. It gives you the Symo hybrid instruction manual in there, also the user manual, or the energy package if you're doing the Fronius battery, or if you search for BYD, there's some specific documents there also for the wiring of the BYD battery. One thing I did want to point out is a lot of the technical, let's say, configurations in this webinar are really relevant for Australia only. They may be relevant for other countries, but we can only talk about what we know is relevant for here, because there is, especially with EPS functions, there is a lot of different requirements that you need in different countries. So They are able to be seen in the wiring manuals. It shows the different countries they're for. So just be wary. Happy for other people in other countries to join in and listen in, except just be wary of the technical content, that's all. Okay, so the Fronius battery storage options, they all focused around the Symo hybrid. So as you can see at the moment, there's 3 options. So you've got the BYD, HV version, the Fronius battery, and the LG Chem version, HV version. And however, what we'll be covering today is just the BYD and the Fronius solar battery, because it's not possible to do backup with the LG Chem at this stage. We are possibly looking at doing it, but there's no timeline, or there's no definitive plans to do that at this stage. Just as it's a little bit more difficult technically to do it with the LG Chem than with the BYD and the Fronius. Okay, so we'll just cover a little about the Symo hybrid, because that's the inverter that you're connected to. So we have what we call multi-flow technology there, which is really going around having multiple power flows at different times and simultaneously through the inverter. So basic functionalities of a PV system, really you have your PV coming into the inverter. That's just feeding the load at first, converts it to AC and feeds the load. Any excess gets fed to the grid. After that, then if you do have a battery, then you're able to store the surplus within the battery. That obviously gives you increase the self-consumption ratio. Also does help the grid in the end. So we're seeing a lot of that happening, a lot of subsidies and things out there, a lot of DNSPs and networks getting very interested in storage in terms of using that to help support the grid. Once you've got storage, so you can charge that from the PV, obviously. So out of the box, what it does is the PV, if the PV exceeds the load, then instead of going to the grid, that'll be stored in the battery. If the load is higher than the PV is producing, then obviously the rest will be taken up with the battery until it's empty. And after that, the rest will go to the grid. So with these batteries and the Symo hybrid, you can charge from the grid. There's lots of different timing sequences and timing settings. You can do that for off-peak charging or time of use charging. So you can look into that. And also, if you've got other inverters on the system, so it may not be a Fronius, maybe a brand X or whatever, that can also be used to charge the battery, either AC coupling or a combination of DC and AC. Okay, so the other thing I wanted to cover just a little bit on is just efficiency. So the reason why we've gone for high voltage type technology is because of the efficiency of the round trip efficiency of the whole system. Because basically the internal bus voltages of the inverters, depending if it's single phase or 3-phase, you're looking around 400 volts or for single phase and 600 for 3-phase. So the closer the DC inputs are to that internal bus, so like say your PV coming in is around 400, 500 volts, or your battery, the closer it is to that internal bus voltage, the better the efficiency is of the inverter. It doesn't have to work so hard in order to boost the voltage up. So instead of going from a 48 volt, let's say battery, to an internal bus of 400 or 600, it's going from around 150 or 400 volts from the battery going into that internal bus. So hence you get the higher round trip efficiencies with that. Also, the current for the battery is a lot lower, so it gives you a bit more flexibility as to where the battery can go. It can be further away, 20, 30 meters away, depending on which battery it is, and still using 4 or 6 mil cables. Okay, so they covered this last time, so there's a few things. I'm not going to go into the details too much of the various battery technologies that we're compatible with. Went through that the last BYD webinar, so if you're interested in that or haven't learnt much about the BYD or the integration between Fronius and BYD, please check out our previous webinar that should be posted on YouTube fairly shortly. So today, as I said, here's a bit of background on the different batteries there. The ones we're going to be covering today, or the integration with the backup function, is the BYD and the Fronius. Okay, so EPS versus UPS. So get this question quite a lot, or even the terms where someone's saying, does it do off-grid mode? We usually don't like to use the term off-grid mode because it does give the impression that the inverter can run off-grid, or let's say without the grid all the time. So EPS, that stands for Emergency Power Supply. It's the abbreviation. What is an EPS? So it provides backup power when the grid goes down. So if the grid goes down and someone's got a battery, then a lot of the time they would like to still have power if that's possible. So usually with a emergency power supply, the power supply is temporarily interrupted. So that can range from a few seconds, 5 seconds, 10, 20, 30, etc., and we'll run through the times with ours. Also, usually inverters, or let's say systems that have emergency power supply, a lot of the time inverters with direct PV ports on them. So direct PV can be connected to it. So for example, hybrid inverters. And what makes it the difference between this is not being able to do UPS is the LVRT functionality a lot of the time, which is your low voltage ride through. So if there's a grid brownout or a dropout, the inverter still needs to stay connected and ride through that. So that is a requirement often for PV inverters, which is then not actually required for battery only inverters. So if we compare that to a UPS, it does again provide backup power when the grid's down. However, it is like a seamless changeover from the grid to backup mode. So you don't even notice that the grid's gone down. So you're looking at less than 20 milliseconds, often 10 milliseconds in terms of changeover time. So you might see a little blink of the lights shortly. However, it doesn't need to power down and then re-power up. It's a direct changeover. Most of the time, the inverters that can do this, are battery-only inverters because they're not subjected to the same LVRT requirements that PV inverters are. So hence, it's easier and more possible for them to do this UPS type functionality. Okay, the other thing is as well backup power. So off-grid inverters doesn't always mean the same as a hybrid inverter. So a lot of you guys out there are probably doing off-grid systems as well. So when you're looking at off-grid system, it's usually for like rural areas, lodges, cottages, and things like that, where you don't have connectivity to the grid, or even if you're in the city, someone who's not wanting to be connected to the grid anymore. Whereas a hybrid system is usually in places where you do have obviously the grid, and that's the main mode when it runs with the grid, and it's there for when you have power cuts is where you can have backup mode type capabilities with that. Hybrid systems are often in their high density PV systems, and also grid operators are really starting to look at hybrid systems a little bit more. When you're designing inverters, there's always, if you're doing something that runs on grid and off grid at the same time, there's always a bit of a, let's say, you got to look at one side or the other, a bit of a compromise. So if you're an off grid inverter looking to do working on the grid, then usually those type of inverters have a lower efficiency than a normal grid connect inverter, or let's say a hybrid inverter. However, they do have better surge capabilities, and they're usually heavier and have transformers. Whereas a hybrid inverter comes from the grid side connection type thing, and that's migrated to doing a backup mode, off-grid type mode. And so in these type of modes, it's very efficient on the grid, but when it's off the grid, then a lot of the time there's limited amounts of time you can run it in the off-grid or let's say backup mode. So just be wary of the different types of uses you may need for your situation. Okay, so the Fronius Symo hybrid, the EPS functionality, so emergency power supply obviously, so it can supply single phase and three phase loads. So the Symo hybrid, which would have been covered in previous webinars, is a three phase inverter only. So my guess is most of the guys that are watching this are aware of what the Symo hybrid is. So can do single phase and three phase loads, as I said. The inverter will detect when the grid goes down and disconnects the site or separates the site from the inverter, and depending what it is, separates it from essential loads from the non-essential loads. And we'll go through that in the circuit diagram a little bit later. So the changeover time for the Symo hybrid is roughly anywhere between 30 and 60 seconds. So it's probably more realistically around the 45 seconds. It will shut down, then the inverter after about that time will start simulate the grid and provide a voltage output. So the voltage output, that is your 230 volts AC coming out on all three phases with your 120 degree phase shift between the phases. One thing to mention, to be wary of, is it does produce a frequency of 53 hertz and not 50 hertz. The reason for that is so that if we have any other foreign inverters connected to the system, that it basically kicks them off. So because it has no way of controlling the output of those other inverters on that small, let's say, island type situation. One thing to mention is that the maximum operating time in terms of its lifetime really is 15% in backup mode. So the hybrid inverter is designed to be on the grid and running on the grid, and only 15% of the time in backup mode. So most of the times, if it's been implemented in the right way, then that shouldn't be a problem at all. Let's say you have maybe a blackout, let's say once every 2 months for, let's say, 4 hours. As opposed to the whole running time of the year, that shouldn't be a problem. So it's mainly that it isn't designed for full-time backup mode in terms of the design. So, okay, so in terms of backup capabilities, so the AC power rating of the inverter is what it can do in backup mode across all three phases though. So if it's the most common one is the 5 kilowatt Symo hybrid, it will do 5 kilowatts across all three phases in backup mode, if there's obviously enough power there from the battery. When it's in backup mode, it can do asymmetrical power, so hence that's why you can do single phase loads or unbalanced loads. A little bit of a snippet out of, we do have a special document on that as well, so it gives you the full description of the emergency power function and its limitations. Just a snippet out of that. So for each inverter, there's a maximum power per phase. So the one probably most likely for everyone here in Australia would be the Symo Hybrid 5. It can do 2080 watts on one of the phases as an imbalance. Okay, so just be wary of that. Most of the time that should suit most of the load. So if you're using a hybrid 4 or a 3 kilowatt inverter, then these limits are then lower. In terms of the power as well, so you need to look at that in certain limitations with that. So it's dependent not only on the inverter. So if it's a 5 kilowatt inverter, then obviously 5 kilowatt is the maximum. However, it is also restricted, or let's say limited or dependent, that's probably a better word, with the battery. So the maximum continuous power depends on the battery. So let's do some calculations. And the reason for this is because both of these batteries are what you call true high voltage batteries. So they have the battery modules in series with each other. So they're not paralleled, they're all in series. So you have regardless of the battery size, it's all maximum of 16 amps input to the Symo hybrid, but each module is 50 volts DC. So for the Fronius battery, it's a minimum of 3 modules to give you 150 volts DC. That times 16 gives you your maximum power. For the BYD, it's a minimum of 5 modules that then, so 5 times 50, then times 16. So you can see an example underneath there. Let's look at the Fronius solar battery 7.5. So that has 5 modules. So your 5 modules times your 50 volts times 16 amps gives you a maximum of 4,000 watts. So it may still be a 5 kilowatt inverter, but if you've got a Fronius solar battery, the 7.5 version, then you'll only be able to get 4,000 watts out of the battery. If you do have PV during the day, that's obviously a parallel input, so you can obviously pull 4,000 watts from the battery, but then as much PV, the same amount of PV through the DC input if you wanted to. And then at that stage, then the AC would limit the output power. Okay, so the Simon hybrid in backup capabilities. So as we said before, this document goes through all the different devices. So the 3, 4, and 5 kilowatt device. We'll just look at the 5 kilowatt one because it's probably the most relevant here. The maximum is then 2,080 watts per phase as a continuous rating. However, it does have a short-term surge rating on there and maximum of 20 amps there. So you can see on the curves there, so what the curve does is if you look at the 4,000 watt curve, that's the one which is taken as the example. That's the light, let's say light blue kind of turquoise type color. So if that means if a 4,000 watt load gets put on one of the phases, we're just talking about one phase, then it will be able to provide that 4,000 watts. However, only for a certain amount of time. And you can see the curve ramping up, so it would be 0.37 of a second. It will be able to provide that power. So the less overload there is, so if you look at the red one, so let's say it's 3,000 watts as a overload power, then it can provide that for a little bit longer. So you're looking at almost 0.6 of a second. It will be able to provide that for. Whereas if you go in the other direction, the yellow line, so if you put a 6 kilowatt load on there, then you're probably looking at about 0.2 of a second. It can provide that inrush type current. So just be aware that there is some limitations. So if you're looking at using this for certain loads, so it's definitely not like an off-grid inverter, where an off-grid inverter, example, take let's say the SP Pro 5 kVA unit, it can do 10 kVA for around 5 minutes. So different types of capabilities for different types of solutions. So what kind of loads would you use? So the backup really should be used for like lights and power. So smaller type power devices, appliances. Because of that rating, that rating limit, you're 2,080 watts per phase. Most of the loads in the house will be single phase, so you probably need to look at that as to what you do. Probably a good idea is to spread the loads across the different phases. Quite often it's all the loads being put on, even though it's a 3-phase site, they've been quite often put all on phase A or phase B. Then in order to get more out of the backup mode, in that, then you'd want to try and separate, spread the loads a little bit there. Ones to be cautious of is inductive loads. So like pumps, compressors, water pumps, etc. They are obviously inductive, so they have a high inrush current or high inrush kVA when they're starting up, which could then trip the inverter and no longer be able to then keep running. Other things as well to possibly be careful of is if you have a lot of switch mode power supplies on one of the phases, they have different power factors with that, so it's not just a resistive load. That can also sometimes affect the capabilities. Okay, so what additional requirements are needed for to get the backup mode? So you may have some Symo hybrids out there, and let's say they've got no battery and you want to add a battery to it, and then they want to do the backup. So in order to do that, the components you definitely need to do the backup is one of the Fronius smart meter. So obviously a 3-phase, that can be the 63 amp 3-phase direct connect, or the 480 volt, or the 50 kA one. Any of those three-phase ones are compatible to use in backup mode. You also need a 4-pole contactor called K1 in this situation. So this contactor should have 3 normally open and 1 normally closed contacts. And we'll go into the details of that later. Then also you need another relay, so a 12-volt DC coil relay with 1 normally open pair of contacts and 1 normally closed pair of contacts. So in total, if the customer doesn't have a smart meter before, you'd be looking at around 7 DIN rail poles in terms of the amount of space needed in the switchboard. So in terms of control cables, so that's usually done with a Cat5, or let's say a high voltage rated, so C-bus cable type comms cable. So you'll need, for the smart meter, back to the inverter, you'll need 3 cores, so D+, D-, and a minus for the Modbus communication. The K1, you need the 2 cores for the feedback. They'll be feeding back to I4 and one of the positive terminals. Then you need the 12-volt driver for the coil, so 2 cores for that. That'll be your IO0 out and then one of the minus poles. And then your K3 feedback is also 2 cores for I5 and one of the positives. So if you added up them all individually, you're getting 9 cores. Of course, we know the Cat5 and C-bus has only got 8. However, you should only need 1 core for the minus, which you would use for the K3 and the meter, and for the plus you can also combine them too. So you should be able to get away with 7 or 8 cores with that. So your one standard cable should be sufficient. Okay, some examples. So the K1 contactor, it can be an AC1 type contactor. So there's contactors have different types. So there's AC1 and AC3. An AC1 is usually for resistive type switching, whereas a K3 has a lot higher inrush capabilities and is designed for switching motors and things on and off. So if you look at the difference between them as well, the K3 type contactors are huge and probably about 10 times the price of an AC1 of the same rating. So these are like miniature type contactors here. It needs to have a 240 volt AC coil or 230 volt if you want it, so it does need to be AC rated coil. As I said before, 3 normally open contacts and 1 normally closed. And you can see the type of pin configuration next to the examples there. So one of the ones that has been used before is ABB. So the EBS 40-31 or the ESB, 63-31, 63 amp one. Depending on how you separate the loads, you could probably get away with a 25 amp one as well. But we run through that in the circuit diagrams. Another option, it would be from Finder. As I said, these are just examples. You don't have to use these. If there's other ones that do the same functionality, there's no problem using those so long as it fulfills those basic technical specifications. You could also get away with some of these a bit trickier to get. If you could also get away with doing a 3 or let's say a 4-pole contactor, 4 normally open with an auxiliary contact, which you just buy separately and clip on the side as you normally close. You can do that as well. Just means you probably take up 1 or another half pole in your switchboard. So these are nice and compact and have them all together. So the Finder one you can get from RS Components, and the ABB one, I think with supply partners do provide some of those, but there's a few other electrical wholesalers you could probably get in touch with to get those. Then the K3 contactor, or let's say relay example. So this is just one here. These are probably a little bit more easier to find. Needs to be a low power DC voltage relay. So the coil needs to be a low power type, 12 volts DC. 1 normally open contact and 1 normally closed. As I said, there's numerous ones out there. This is just an example. It's 1 pole wide. and as you can see, the pin configuration there, or the switch configuration, contact configuration. Okay, so what's the purpose of these? Just to give a bit of a rundown first, and we'll go through that when we go through the circuit diagram as well. The purpose of K1 is when the grid's down, it provides separation from the grid for the backup mode to take place. So it disconnects the whole site from the grid, or disconnects the inverter and the essential loads from the grid. So that's what, depending on how you've configured it, but that's one of the things, and we'll, as I said, we'll go into more detail once we see the circuit diagrams. It also provides feedback to the inverter to let it know, okay, I'm disconnected from the grid, I'm allowed to start up in backup mode, and that's the normally closed contact. So the purpose of K3 is the data manager is obviously it's using its digital outputs on there. So these digital outputs are just 0 or 12 volts, and there's pretty low power coming out. So it's not enough to drive a contactor coil of, let's say, 12 volts if we used a direct contactor. So what it does is it's to assist the activation of the K1 coil, because the hybrid manager or data manager, as I said, can only provide 12 volt DC drive signal. It also, one of its contacts is it disables the automatic functioning of K1 again when the grid comes back up. And that'll make more sense once we start looking at the circuit diagram. So that happens once it's, when it's running in backup mode. Okay, so in terms of wiring, so wiring from the data manager to the various coils and contacts. So we start here with the plus terminal. Would need to go to one of the closed contacts of K1 in order to provide power for it to signal some of the signals coming back to the hybrid manager. I4, so input 4, is connected then to the other side of that closed, normally closed contact. And as you can see, it's also connected to one of the side pins of K3. Then you have IO0, so that's output 0, so that goes out, and that's to drive K3 coil. And then you have the I5, which is an optional input, which will again make more sense once you look at the circuit diagram. And then K3 also comes from the negative of the meter there. So you can see L1 is connected to one side of K1's coil, and the other side of that coil is connected through one of the contacts of K3 and then through to the neutral. So we'll go through a little bit more of that once with the circuit diagrams, it'll make more sense. So in terms of the hardwiring, once you've got the hardwiring done, then you need to commission the actual system. So I'm not going to run through how to commission a data manager or a hybrid manager. They're covered in other webinars and other training material. So where the assumption is that that's all been done and the system's up and running, and all you're wanting to do here is purely configure the EPS mode. So you would activate the Wi-Fi access point on the inverter, connect it to that Fronius network, which will be a Fronius _239, and then whatever the data log ID is. Open the browser, type in the standard IP address, your 192.168.250.181, and then that'll bring up the web page that you see here. Then you would go to settings on the right-hand side. Then once you're in settings, you want to go to IO mapping. So you go on the left-hand side there and select IO mapping. In IO mapping, that gives you the picture here. And what we're doing here is we're configuring the IO outputs and inputs of the hybrid manager in order to get the signals, send the signals out and get the signals back in in order to enable and start up the emergency power function. So you need to enable that. So that's a little tick box there because that's not turned on by default. You need to tick that little box there. And then once you've done that, you go to the save button, which is at the top right there with the tick and the cross. and you hit that. Then it'll come up with a screen saying your settings have been saved. So once we've done the I/O, then you scroll down the screen there and you want to go to energy management. So you select that, and then and the following screen will pop up. So on this screen, you've got things you can do, your own consumption, you can do optimization there, you can set it to manual, so if you want to manually charge the battery, you can do things like that as well. But in this section, you can see there's the emergency power settings, and this is what we want to go to. So in this section here, that's default to off. You want to select automatic on that as the first thing, and then secondly, you want to choose your remaining battery capacity. So this is defaulted at 7%. So depending on, and what this means is in order to do backup, you need to have some energy stored in the battery. So, if the battery is flat and a backup, like the grid goes down and the battery's down, then obviously it's got no power in order to do that. So this is one of the things that some people forget, or is when you're doing backup systems, is you do need to sacrifice some of the usage, the daily usage of the kilowatt hours and the storage of the battery. So this is where you can set, okay, and what point with the normal discharge and charge usage during the day, and offsetting your nighttime usage, etc. At what point, how far should that go down? So in this particular example, we've got it set to 20%, which means that the battery will only discharge during the day, be it to loads or where else, only down to 20%, and that's it. It'll hold that percentage at 20%. And so when it goes into backup mode, then it has a bit of remaining capacity in order to provide backup in case the battery is down low. If it's higher than that, like if it's been charged up, then that's fine. There's no issues there anyway. But yeah, in the case where you may be using the battery quite often and using all its capacity, you might want to keep that in mind. So it's always a bit of a toss-up. You need to decide what's more important for you, and then you can dynamically change that. Then the SOC warning level. So what that is when you are in backup mode, so it's gone into backup, and it's allowed us to go below the 20%. Then what you can do is you can get a warning sent to you. So either the web interface, or if your router's working, etc. with the power, it'll send it to SolarWeb as well. It'll send you a warning that when a certain SOC or state of charge level has been reached. So let's say you're in backup mode, you're starting to drain the battery. Obviously, you're going below the 20%. Once it hits 10%, it'll notify you that, okay, you're getting close to the battery being flat. So you can freely set that to what you want as well. So you set those three things up there, and click Save button on the right, and that will save those settings for you. Okay, so that's all you need to do on the data manager, so on the hybrid manager in this case, sorry. After that, then there is some settings on the inverters displayed directly that you need to do. And what you need to do, you need to activate the alternate setup. So when it's running in grid connect mode, if you've set it up right, then you should have set up AU for Australia. And so that's the AS4777 settings. So, it looks at the frequencies and voltages and all those functions. But then what it needs to do when it goes into backup, it needs to know what kind of other frequencies or voltages should I be doing. So in this case, you need to enter this special code. So you press the third button from the left 5 or 6 times, depending on which menu you're in. That'll pop up with your 5 zeros, and then you need to enter the code 39872. That'll get into the menu, and you see select alternate setup, and you need to select EP50, emergency power 50. So you also see setup AU, Australia and things in there. You don't set it to AU because this is an alternate setup for the emergency power function. So you need to do this, otherwise it won't kick in when the relay is telling the data manager what to do. All right, so we'll get into looking at the schematics. So this might hopefully assist in looking at how this all works. So this diagram here is a picture of all the relays and the contactor setup and they're in the rest position. So there's no power on anything. Inverter's turned off, grid's turned off, everything's just as you would see with no power on anything. So let's see, I hope you can see my cursor here a bit. So you can see here, this is the grid coming in, obviously 3-phase, L1, 2 and 3 coming in, your DNSP meter, and then you've got here the Fronius smart meter. You've got K1 here in terms of your contactor. Here's your loads. Here's your inverter connected here. Then you've got your auxiliary, or the normally closed contact of K1, normally open of K3. Here's your actuation coil of K3. Here's the coil of K1, and then here's the normally closed of K3. This is a fuse, or it could be a circuit breaker here. It's just to protect the coil there. This does have RCDs written in there, so this just depends on how you're doing the system. So it doesn't mean you need an RCD or require an RCD, because there's a lot of talk going on about that at the moment, if it's required or not, with different things depending on what type of mechanical protection you do. But take this as being an RCBOs, or it could just be circuit breakers in this spot here. So okay, so as you can see here, the K1 coil here has no power on it, and neither does K3. And then you can see, so this is your normally open contacts of your K1, so the 3 normally open contacts, and then this is your normally closed contact here of the K1. K3 is also off, as I said, and so normally closed is here, and then you have normally open feed. This is the feedback. So both of these 2 contacts are what we call feedback contacts, and they're to help let the data manager or the system know, am I actually in the position I'm saying I'm in terms of the contactors. Okay, so we'll look at this case here. So this mode is in, let's see, so I didn't change the heading on that, sorry about that one. So this is actually, the heading's wrong on this one. This is grid, where the grid is actually there, on there. So you can see the power in the red labels here. You've got the power coming up here, and all coming in through here. This K3 contact here is normally closed. So this is closed, so as soon as L1 gets a bit of power here, it actuates this K1 coil. So you can see one side is connected to neutral, the other connected to L1, and so that activates and pulls in K1. So that closes the contacts here. So your 3 normally open contacts have just closed, and inversely, your normally closed contact, this K1, is now open. Okay, so in terms of, you can see here, your coil, K1 is on, normally open is closed, and normally closed is open. Your K3 is off. In this case, there's no power to that, so it's in its normal position. So normally open is open, and normally closed is closed. In terms of the hybrid managers, the inputs on here and the feedbacks may be a little bit difficult to see on here, but this pin here I'm pointing to at the moment, the top left one on the data manager, that is the plus pin, so it's a plus 12 volt pin. The next one down is your I4, input 4, and the one down after that is input 5, and then underneath that is negative. Then you got IO0, and this is your Modbus communication here, so D plus and D minus. Okay, so all of these 3 are off. And as you can see, these contacts pull in, the inverter is running in grid mode and providing the loads like it normally would. Okay, then when the grid goes down, so the grid's failed, it's turned off, what happens is the K1 coil here is disconnected, so the power to that has gone off. So you can see L1 is missing, whatever. So that's turned itself off, and this opens here, so your K1 coil opens up, and then on K1 the feedback here, this connects together, so this shorts itself together, and what you're doing there is you're pulling this positive pin, you're joining positive 12 volts, and you're putting that onto input 4. So that's sending input 4 an input signal of on, and what that on is, that's the request for going into backup mode. Okay, so once that's then gone in, then the next thing would be is that K3 here gets activated. So that'll be put out with 12 volts. So your IO 0 here, this is an output. It gets told, okay, I'm going to go up to 12 volts, puts positive voltage on here. The other side of this K1 is on the negative pole, and so that activates this K3. So the K3 gets activated, so this opens. So now this normally closed terminal here is open, so it's breaking the path from your active and neutral to this coil, and it's also closing on this pin here as well. So it's sending a 12 volt signal to I5 as well. So I4 is high or on, and I5 is on. Okay, so once that's done, then the inverter will start up in backup mode. Okay, so these feedback coils, so we need to know the feedback coil for K1 first is basically signaling, okay, the grid's gone down, but has the K1 physically opened or moved? Because it's a contactor, it's a mechanical device. You know, what happens if it's welded shut or something? The grid might go down, and you don't want the inverter starting up in backup mode if the grid isn't totally physically disconnected. So hence when this physically moves and opens, that's why you've got an inverse physical connection back to the data manager in order to provide that feedback. Same goes for K3. It may have been told to turn on, which is the main reason for turning this on is to activate this contact here to disconnect it from the grid, because what happens if you don't have this open here and the grid comes back on, what will happen is this coil will get 240 volts straight away as soon as the grid comes on, which will then pull in this contact here, and that'll do that while the inverter's running in backup mode. First of all, it's running at 53 hertz, and secondly, it has no phase synchronization with the grid. So you could get an out of phase connection between the grid and the inverter, which causes a big bang. So hence that's why these feedback coils are there. Okay, so and again, then once it goes, if we go back to, and the grid comes back up, and I'll go through that in one of the next slides. So these slides here demonstrate, so I don't have any separated loads. This is just showing all the loads of the house, so it's showing the complete house. Now we'll do a bit of analysis of it with the separated loads. So everything looks the same, all the contactors are the same, except in this case, before the K1 contactor, you have loads breaking off here. So these are what we call non-essential loads, or your standard loads, and then these will be your backup loads, which are on the load side of the contactor where the inverter is. Okay, so when this contactor opens up, then there's no grid here, so all of these loads at the top, none of these will be supplied. Okay, only the ones below here, which is probably more recommendable if it's possible to do that. However, it's not an absolute must. It just means that if you don't do it this way, you don't separate them, you just need to be more wary of what loads you are trying to back up. Okay, so with the grid present, so you can see here all the power coming through, just like in the diagram before. K1 is on, which is then has this K1 contacts are pulled in. The normally open contacts are pulled in. Normally closed is open, which we have here. Inverter's running, so inverter's in grid connect mode, and all the loads are being supplied by the grid and the inverter, and it's just balancing out with the power. So you can see here, K1 is on the coil. The normally open one is inverse, so it's closed, and the normally closed is open, etc. And all the inputs to the data manager, they're all off. Then if the grid disappears, what happens is then this opens up, so the K1 loses its power, the K1 coil. This contactor opens, so when that's open, this then closes, your K1 feedback. It tells the data manager, hey, I'm requesting to go into backup. The K1 contactor is open, I am disconnected from the grid. Then when that connects, then the data manager says, okay, all right, turn on K3. K3 turns on, which disconnects, which opens up this contact here, which is the power to the K1, and also the feedback K3 also tells the data manager, hey, the K3 relay has actually physically moved to the right position. And okay, away we go. Let's start in backup. So you can see here all the other loads that were on the top here. These are not being provided because this K1 contactor here is open. You're only supplying your backup loads here. Okay. All right. So what happens when the grid does return? So we're in backup mode and the grid returns. So obviously you get voltage and frequency there. What happens there is you see the smart meter. Here's the K1 contactor. The smart meter is connected on the grid side of the contactor. And the reason for that is when the grid comes back, it powers up and says, okay, all right, and it starts delivering values or data to the inverter. So the inverter says, okay, all right, I'm getting data. So it looks at that, says, okay, the grid could be up. It analyzes the data, but it only analyzes the voltages, the grid voltages there. And if they're within the set limits, so your normal Australian AUS 4777 limits, voltage only, then it will say, okay, I'm satisfied with the grid being there. I'll turn EPS mode off, and then we go through that cycle again. So turns EPS off. It will then turn off K3, which then closes K3 contact here, allows power to K1, pulls that on, then K1 contacts get pulled in here, and then the grid and everything is supplied to the inverter, and it goes through its normal 67 grid test timer and starts back up in grid mode. Okay, so hopefully that description was clear enough in terms of how it works. So there's a bit of stuff going on in there. So we're actually lucky, to be honest, with our configuration, what we have here in Australia, because as you might have seen in some of the previous drawings there, that the neutral is not being broken. The neutral has to stay connected, and hence also the MEN remains intact. In other countries, it's a requirement to remove the neutral or disconnect the neutral. And in those cases, you then need to reconnect the MEN to the neutral in the backup mode, and that needs to be redundant. So you have relays all over the place, and so it's a lot more complex and messy. So for once, we're actually got an easier solution than everyone else in Australia. Okay, all right. Well, what we might do is cover some Q&A. So I might hand over to Ryan and see if there's any questions there that I might want to cover. I mean, he's been answering some via the chat thing there, but let's see if there's anyone who's got any others.
Sure. So we've got one unanswered here from Josh Shepherd. So it says, you're wiring a feedback to the inverter using the normally closed contacts. How is this legal, putting the ELV signal wires with no separation to power? So I guess it's only 12 volts, isn't it? But
so the ELV is separated to the power. So the separation would be through, you could use heat shrink, I guess, but the cables that you've got there, it was no different to having the smart meter cables really in the switchboard. All the switchboard, all the ELV needs to be rated, or the cabling needs to be rated at the highest voltage, which is then obviously 240 volts. Not sure if that covers your question with that. If not, then I'm happy to take that up later.
Okay. So Graham Malone said, be careful of some of the components from RS, as some aren't approved here for use in Australia. I know the ABB contactor is.
Okay. All right. Thanks for that tip. Yes, that's one thing I didn't look at. So yeah, thanks for that. So yeah, if you are looking at some of these devices, may not be. As far as I've checked with the ABB that it is usable in Australia. And the Finder one, that's maybe something we need to check on that as well, yeah.
Okay, so we've got Jeff Drew, who says, what happens to K1 coil if you lose one of the phases, so say one of the lines goes down?
Okay, so if one of the line goes down, what will happen there is the inverter, so if it's if it's L1 that goes down, obviously the contactor will open up. But if it's L2, and then it'll start going into backup mode. Because the meter needs to have all 3 phases within spec, then it will go into backup mode with that one. If it's L2 or L3 that's missing, then it actually won't go into backup mode. The inverter will switch off. Because it needs to have all 3 phases to be running. However, it won't go into backup mode in that case.
Sure. So we're going to see a grid error.
Yeah. So you'll see on the inverter, you would see a grid error on there. It will come up with a 103 most likely, saying that one of the phases is missing because the 3-phase inverters in Australia need to have all 3 phases present and within spec in order to operate.
So Aaron says, when will we see the Primo hybrid?
So yeah, it's a pretty typical question. So the planned release date is around October, November this year. If any of you guys are heading up to Sydney next week for the show, then yeah, feel free to come past the stand. We'll have one on the stand there to show you. But that's the planned date for the single phase. That will be coming to 3 to 6 kilowatts as in power.
Sure. So we've got Martin, who has said, when will we see the 3-phase hybrid get 2 MPPTs?
So with this particular model, we won't have it on the current Symo hybrid. The first off the rank in terms of the new inverter generation, or to complete the range, is as I said, the Primo hybrid that's coming in October, November. Then planned for January, February is the plan. Let's see, hopefully it goes to plan. Is the larger Symos, Symo hybrid. So it'll be the Symo hybrid 6 to 10 kilowatts, and in the new style type inverters. And then after that, we're looking at doing. We probably will then upgrade the older Symo hybrids to the newer style. That'll be the lower one, so the 3 to 5. So that'll be when it's coming in the having a dual tracking on that. So, but this particular model won't be changed anymore. Yeah.
Okay. So we've got a question from Michael King, who says, why are all manufacturers doing hybrids with EPS backup, which only covers partial wattage, when you've already got available AC coupled solutions with contactors with separate battery inverters, which could keep on the sort of total wattage in grid connect inverters?
So I think I'm not quite sure I understood the question, but I'm guessing maybe talking about
comparing
having
it to
the extra the extra power. I think is he maybe meaning if it's to get the extra power of it, so like having an AC coupled system?
Yeah, I think he's like trying to compare it to, he was previously talking about SP Pros and Sonans, so I'm guessing in comparison, why would you have a hybrid instead of going with an AC coupled solution?
Well, I think there's some advantages with a hybrid, depending on the size as well. You often have, depending on which AC coupled system you have, I mean, some of them do full off grid, like an SP Pro. Obviously, that can it can only do AC coupled. The DC coupled one, some of the advantages of that would be through the utilities requirements. So you can have then a bigger, let's say you have an 8 kilowatt, or we're looking at bringing out a 10 kilowatt hybrid as well for a single phase. That would you be able to do have the full power on that. Whereas if you have and also get a lot of PV into the battery through that. Whereas if you do like an AC coupled, let's say you have a 5 kilowatt Primo and let's say a Tesla Powerwall or some kind of 5 kilowatt AC battery, it makes it you may not be able to get all the power into that you need. So you're only limited to a maximum of 5 kilowatts into it. Whereas with hybrid, in the background through the DC internal coupling, you can get higher power and more power into the battery.
So we've got one just coming from Richard, who says, so if you lose one phase, the inverter shuts down. Does the EPS kick in then, or only if the coil phases all go down? So I'm guessing he means if one line goes down.
Yeah, so that was a similar question to before, but I'm happy to repeat the answer. So if phase 1, so L1 goes down, then that's the one which is actuating the coil. So that means that the coil will open up and the whole process of starting backup mode will be triggered, and the inverter will go into backup mode, and it won't come out of backup mode until that first phase is back, because the meter data, it's, as I said, that's sending through. If it's missing one of the phases, it will show that one phase is out of spec, and so it says that the grid's not okay yet, and so not to come out of backup. If, however, it's L2 or L3 that fails and is no longer there, or just even one of those, then the inverter will not go into backup. The K1 coil will still stay pulled in, and the whole site will still be connected to the grid. However, the inverter will shut down even in grid connect mode, but it won't try and start up in backup mode. So that is a scenario where you wouldn't get backup in that case.
Okay, so we've got a question from Tim who says, what are the ratings suggested for the F1 and F3? I'm guessing you mean K1, K3?
Yeah, so there's probably, for the coils, it's just whatever the coil's rated at, I guess. So, I mean, just a 1 amp thing, or depending, again, that's an AS 3000 or 3008 rule, I guess. You need it, it's purely to protect the cable. So whatever cable you use, if you use a thicker cable, then obviously that fuse rating would be higher. If you use a thinner cable, then it would be lower. So it's purely to protect the cable.
Sure. So that looks like it's it. If you've got any more questions, get them in quick. Anything else you want to close with, Rod?
I don't think so at this stage. So yeah, if anyone's interested in the BYD webinar, we did one gone on a month ago now. So that runs through all the commissioning, the advantages, etc., of the BYD solution. At the moment, we're in a soft start phase. So if you do want to get the BYD up and running, it will need a remote software update on the inverter, and to do that, you just need to contact our technical support, and they'll get the data logger ID unlocked for you, which will then allow you to download that software in order to implement it. So we do see, I think we'll see quite a few more batteries going in with this new BYD solution, and looking forward to seeing a few more storage systems going in.
Awesome.
All right. Well, I think we'll leave it at that. There's been a few questions there, a few good ones and things. I hope today's webinar has been useful for you. If you do have any more questions or like any more information about it, feel free to contact us at the Fronius headquarters here. Send us an email or ring us up, and I'm more than happy to go through things. As I said, there'll be more and more information on the web and on our website on how to do things. One of the tips as well to look at, apart from our normal manuals and things we have, is to go into the technical support section of the website, and in there's a lot of really good white papers and quick guides, which where we've tried to explain the manuals a little bit with a bit more pictures and pointy things, etc., to give you a bit more assistance in doing that. So feel free to check that out, and otherwise, thanks a lot for attending, and yeah, look forward to catching you guys at the next webinar. Thanks very much.